So we've got an asteroid, a little tiny planet. Ceres is, I believe, the biggest of the asteroids. It's like a little tiny planet. 500 kilometers in radius. So not that big. And but we want to know what is the acceleration of gravity on its surface and how much would an 85 kilogram astronaut weigh on its surface. Okay, so let's do that. So given, so we've got a little asteroid here. And I believe the spaceship Dawn is on its way to Ceres. It's going to take some pictures of it. So that'll be, I think it's going to get there in the next year or two. So anyway, so here's an astronaut standing on the surface, not drawn to scale. And so we want to know what is the acceleration of gravity on its surface. So find G, and then for part B, we want to know what is the force of gravity or the weight of the astronaut. So let's solve this. Well, here it is. Force of gravity equals mg, but the force of gravity is also equal to g times the mass of the planet times the mass of the asteroid divided by the radius or the distance between the center of the planet and the center of the astronaut squared. And this is really just the radius squared. And we're looking for, so look, the mass of the asteroid, the mass of the astronaut doesn't matter. It cancels out. So this allows us to solve for G. So all I have to do is plug these in, and I'll get it. So G equals big G. The mass of the asteroid, which is given to be 7 times 10 to the 20 kilograms. That may seem big, and it is big compared to us, but compared to the Earth, it's tiny. Earth is 10 to the 24, so it's what, 1/10,000th the mass of the Earth. And then we have to divide by its radius squared. But what does this radius have to be in? You always have to do things in meters. So just say, hey, the radius here, oh, I didn't put it in what's given. The radius here is 500,000 meters. You have to put it in meters. Okay, and then I didn't put the mass in what's given. So, hey, there's your mass right there. And then we have to square that. So we're going to take 500,000 meters, and we're going to square it. Oops. Yeah. And then, so you got to plug all that into a calculator. And when you do, what is it? What do you get? 0.2?
I use 500.
Huh? Oh, I use 500. Yeah, that's going to be a problem.
Yeah.
How many of you used 500? Oh, come on, people, come on! It's got to be in meters. Oh, you didn't square it. Yeah, you got to square it. You got to square it. Well, if you do everything right, you get 0.2 meters per second squared. Now that's for part A. Now what you have to do is, well, what is the weight of the astronaut? Well, this is really the gravitational field. You can kind of think of this, I actually prefer to write this as 0.2 newtons of force per kilogram of mass. That's the better way to write what G is. I'll accept either. This reduces to meters per second squared, but I prefer this. Well, now to figure out how much the astronaut weighs, force of gravity is just equal to m times g. So that's going to be 85 kilograms times g, which is 0.2 newtons per kilogram. And your answer should round off. Now, maybe you kept this with more significant figures and you carried it over here and multiplied. If that's what you did, and that's why your answer's a little bit off, no problem. I'm not going to mark that wrong. But so the force of gravity here, 0.2 times 85 would be, I think it's 17, right? 17 newtons. Or did some of you get 16? Those of you that did it right, huh? 15.8? I'll round it to 16 newtons. I think that's what I wrote in my book, that it was 16 newtons. I'll give it to you. I think it's just rounding off. Now, hey, so, well, anyway, hold on a second. This is the whole problem right here. And that is how, now, hey, wouldn't it be awesome to be able to walk around on series? You're on a world. You're on a little tiny world. But your strength on this world would give you almost superpowers. You would be able to leap tall buildings in a single bound. It would just take you 20 minutes to do it. I mean, you would jump, and you could jump with an acceleration of gravity of only 0.2, a weight of only 16 newtons. With your strength in your legs, you would be able to jump so high. You would easily be able to jump over this building. Easily. In fact, you would jump up and you would go, oh, rats. I got to wait 20 minutes for me to come back down.
You just fly off.
I don't think you would be able to reach escape velocity from Ceres by just jumping. There are asteroids that are small enough where escape velocity is slow enough where you would be able to jump away from it and not come back. We're actually going to do that. The juniors will the last 2 weeks of school. We're going to talk about escape velocity and that sort of thing. And we also cover it in AP Physics quite a bit. All right. That is all.